Hello students, welcome to Educate. Today we are going to solve the numericals based on kinetic theory of gases. So we have already studied about the basic concepts related to this chapter. Now we will try to solve some important numericals based on this chapter. These questions have been taken from NCERT. Question number 1. Estimate the fraction of molecular volume to the actual volume occupied by oxygen gas at STP. Take the diameter of an oxygen molecule to be 3 angstrom. Angstrom, I think you remember, it is 10 power minus 10 meter. Right. So let's see how to solve. Question number 1. Here, if you remember, one here at STP, the volume will be equal to 22.4 liter, means 1 mole of gas has volume 22.4 liter. This can also be written as 22.4 into 10 to the power minus 3 meter cube. Now, here we are going to consider the volume. If a radius is given, radius here it is diameter, so 3 by 2 angstrom. So let's find out volume otherwise. So volume will be equal to 4 by 3 pi into r cube. So r cube means 3 by 2 into 10 to the power minus 10 whole cube. Right. Into we are considering at STP and we are taking molar volume. Here 1 mole. So 1 mole means we write Avogadro's number 6.022 into 10 to the power 23. Now we can simplify it. 4 upon 3 into 22 upon 7 into 3 into 3 into 3 divided by 2 into 2 into 2 into 10 to the power minus 30 into 6.022 into 10 to the power 23. Now we can simplify. So this will come out to be 6.78 into 10 to the power minus 5 meter cube. Right. Now, what is our concern? Our concern is to find the ratio of the two. So let's denote it as V1 or V2 or just write ratio. So a ratio, we take this as numerator 6.78 into 10 to the power minus 5 divided by this 22.4 into 10 to the power minus 3. We can simplify. So 6.78 divided by 22.4 into 10 to the power minus 5 plus 3. Right? We can further simplify, and this is around 3 times you can cut it when you remove decimal. So this will be 3 into 10 to the power minus 3. I think thing is clear. Now let's see next question. Molar volume is the volume occupied by 1 mole of any gas at standard temperature and pressure. Show that it is 22.4 liters. So let's evaluate it. Standard temperature and pressure means what? T is given, T equal to 273 Kelvin Pressure is given 1 atm 1.013 into 10 to the power 13 into 10 to the power 5 Pascal, right? And STP, and value of R, R equal to 8.31 joule per mole per Kelvin, joule per mole per Kelvin, and you know the equation PV equal to nRT. Here we are considering 1 mole, so PV equal to RT. And here what is our concern? We have to find out what is the value of V. So we can say V equal to RT upon P. We can put the values. R is 8.31 multiplied by temperature is 273 Kelvin divided by pressure. Pressure is 1.013 into 10 to the power 5. Now what all is left is to evaluate. So if we evaluate it, this comes out to be 0.0224 meter cube. And if you remember, here 1 meter cube is 1000 liter, 1 meter cube is 10 power 3 liter. So in place of meter cube, we can write 10 power 3. So 0.0224 into 10 to the power 3 liter. We can shift decimal places forward because of this positive power. So we will get 22.4 liter. So it is simple question. Now we are going to see next question. So let's see what does it say. We are going to see fourth question. Question number 4 says, an oxygen cylinder of volume 30 liter has an initial gauge pressure of 15 atm and a temperature of 27 degrees centigrade. After some oxygen is withdrawn from the cylinder, the gauge pressure drops to 11 atm and its temperature drops to 17 degrees centigrade. Estimate the mass of oxygen taken out of the cylinder. Take R equal to 8.31 joule per mole per Kelvin and molecular mass of O2 is 32 unit. Question is not tough. So here we have to do some basic analysis. So we can apply formula P1 V1 equal to P1 V1 equal to nRT1, from where we can get, let's write it N1. So N1 equal to P1 V1 divided by RT1. Similarly, P2 V2 equal to N2 RT2, which will give N2 equal to P2 V2 divided by RT2. This is how we can find the number of moles. And then, since some moles have been taken out, so we find the difference N1 minus N2, right? And to find the mass, we multiply it by molar mass, and that is given in the question. It is molecular mass, that is 32. So this is all to be done. So let's calculate one by one. So to get N1, what do we need? We need pressure P1. So P1 is 15 atm. So you can write 15 into 1.013 into 10 to the power 5 P1, then V1. V1 is volume is 30 liters, so you can write 30 into 10 power minus 3 meter cube whole divided by gas constant 8.31 into temperature T1 27 degrees centigrade. So 27 plus 273. So this will become 300 Kelvin. So this is value of N1. So this comes out to be 18.3, right, moles. Now we consider this equation from here N2. Here P2 pressure decreases to 11 atm. So 11 into 1.013 into 10 to the power 5 into, what about temperature? Temperature drops to 17 degree. So 273 plus 17, 273 plus, but here we have to write volume at this point. So this is P2 and then V2. What is V2? 30 liter. So since gas remains in the same cylinder, so it will remain 30 into 10 to the power minus 3 divided by gas constant 8.31 times temperature is 17, means 10 degree less. So this is just 290, right? So again we evaluate it. So it will come out to be 13.8 moles. Right. So we have got N1 and N2. So we find here N1 minus N2 into molecular mass 32. So this will become how much? This will become 18.3 minus 13.8 times 32. So if we evaluate this 5, then 4, 4.5 multiplied by 32, we can further multiply to get the result. So this is simple. Let's see next question. Here, next question says, an air bubble of volume 1 centimeter cube rises from the bottom of a lake of 40 meter deep at a temperature of 12 degrees centigrade. To what volume does it grow when it reaches the surface, which is at temperature of 35 degrees centigrade? Here, what you notice, is pressure same? No. So you have to find out pressure. So like what is P1? So P1 is 1 atmosphere. 1 atmosphere means 1 atm or 1.013 into 10 to the power 5 plus pressure due to liquid column. So here 40 meter deep. So rho Hg 40 into G is say 9.8, and the density of water you can take 10 power 3, right? So this is P1. Temperature is given T1 as 12 degrees centigrade. So 12 plus 273 Kelvin, right? What about T2? T2 is 35. So 35 plus 273 Kelvin, and what about pressure? So obviously it comes on the surface. So P2 will be just 1 atm, sorry, into 10 to the power 5 Pascal. Okay, so here our question is, initial volume is given 1 centimeter cube. V1 is given as 1 into 10 to the power minus 6 meter cube, and V2 is to be found. So we can easily evaluate, we can apply the formula P1 V1 divided by T1 equal to P2 V2 divided by T2. Our concern is to get a V2, so we can write V2 equal to P1 V1 into T2 divided by T1 into V2. So let's write the values. V2 equal to P1. So P1 this much. So that is 1.013 into 10 to the power 5 plus, let's write it as 10. So that will make things easier. So this will become 400 into 10 to the power 3 P1, then V1. V1 is given as 10 power minus 6 into temperature T2. T2 will be equal to 2. This will become 8, 308, 35. This is 8, 0. And this is 308. All right. And divided by T1. What is T1? T1 will be 285 into V2. Not V2, because we have to find out here this, here our concept P1 V1, this is P2 instead of now, so we can write P2. P2 is 1.013 into 10 to the power 5. Now you can evaluate it, and after evaluation you will get as 5.3 into 10 power minus 6. It will become 5.3 into 10 to the power minus 6 meter cube. Right? So I think you have understood. Let's go to next question. Next question says, estimate the total number of air molecules inclusive of oxygen, nitrogen, water vapor and other constituents in a room of capacity 20 meter cube at temperature of 27 degrees centigrade and at 1 atm pressure. So let's evaluate it. So we can write the relation PV equal to nRT. If we don't write R, then what can we do? In place of R, we can write Boltzmann constant times Avogadro's number. Then again calculation can be done. And here our concern is to get the value of N. So if we write N, then N equal to PV upon RT. Or we can write PV divided by, in place of R, we can write Boltzmann constant into Avogadro's number. We will get same thing into temperature. So let's put the values. But here our concern is to get total number of molecules. So we can take this here. So N times Na will be total number of molecules. Then what will be left in RHS? That will be Kb times T, right? And then we can put the values. So in our question, information is given that capacity means is 25 meter cube and temperature is given and pressure is given. So it is simple. So 1.013 into 10 power 5 into volume. Volume is 25 meter cube divided by this value 1.38 into 10 power minus 23. So 1.38 into 10 to the power minus 23 into temperature. Temperature is given as 27. 27 means 273 plus 27. To convert it into Kelvin, it will become 300. We can evaluate it, and this will come out to be 6.117 into 10 to the power 26. I think you can easily do. Let's see next question. Next question says, question number 7, estimate the average thermal energy of a helium atom at room temperature 27 degrees centigrade, the temperature on the surface of sun, that is 6000 Kelvin, and the temperature of 10 million Kelvin, the typical core temperature in the case of a star. So obviously kinetic energy or thermal energy depends on temperature. In three cases we will see that energy is increasing and it will be highest in the third case. So let's apply the formula. So average energy E is given by E equal to 3 by 2 kBT, where kB is Boltzmann constant. So if we evaluate it, so 3 by 2 into 1.38 into 10 to the power minus 23 into temperature, and temperature here is given, this will become 273 plus 27, 300 Kelvin. And then we can evaluate, right? So it will come out to be 6.21 into 10 to the power minus 21 joule, right? Now let's increase the temperature to 6000 Kelvin. So here let's denote it as E1. So E2 will be again 3 by 2 kBT. So 3 by 2 into kB, 1.38 into 10 to the power minus 23 into 6000, right? Because T is this time 6000, and we can evaluate it. So this will come out to be 1.242 into 10 to the power minus 19 joule. Now let's see the third situation when temperature increases to 10 million Kelvin. So 3 by 2 kB, that is 1.38 into 10 to the power minus 23 into temperature is 10 million. 10 million is 10 lakh, 10 power 6, and this is Kelvin, right? Then we can evaluate it. So we will get how much? This time its value will be larger, 2.07 in 10 power minus 16 joule. So you can evaluate it, and this is how you have got the result. Now we are going to see next question. Next question says, question number 8. It says, not 8, this is theory question that you can do. I'm doing this one. At what temperature is the root mean square speed of an atom in an argon cylinder equal to the RMS speed of the helium gas at minus 20 degrees centigrade? Atomic mass of argon is 39.9 U and that of helium is 4 U. So we can apply the formula. So V is given by V equal to 3RT upon M, right? So two cases we have to consider, and we will write. So suppose we write for helium. So helium 3R into temperature. What is temperature of helium? Is minus 20 degrees centigrade. So we can add 273 and then we will get 253 Kelvin divided by mass of helium is given as 4. So we write it as 1 and then V argon we consider. So 3R into T. So what about its temperature? If it is 2B form, then we can write T here and then its mass is given as 39.9. But in our question, it is given that these two have the same speeds. So V helium is equal to V argon. So we can say, we can square them to remove the root. So 3R divided by 4 times 253 must be equal to 3RT divided by 39.9. 3R will cancel out and then what will be left? So we will be left with T equal to this 253 multiplied by 39.9 divided by 4. We can evaluate it and it will come out to be 2523 Kelvin. So this is how numericals, the important numericals of this chapter are over. Thank you for watching. Team Educate.